The challenges of space require a variety of tools. We'll discuss here an approach to propulsion that shows great potential, but holds particular promise for aerospace applications. Modern rocket technology is extraordinary, capable of delivering over 60 tons per launch to low Earth orbit. It is the workhorse enabling us to regularly reach and operate in Earth's orbit and beyond. But it does have its limitations. All rockets depend on an exhaustible fuel supply, and refueling in space is very uncommon. Once a rocket's fuel is spent, it is out of luck, paralyzed and adrift with no way to reacquire the ability to move. So we are looking for a renewable method of propulsion. Something that can acquire power from a renewable source, like a solar panel, and deliver a sustainable thrust, even just a little, to maintain a craft's functional operation beyond its exhaustible fuel supply. So let's start with something small. Imagine we have a conductive wire and provide a charge to that wire, in this case, positive. That charge will give rise to an electric field in the vicinity of the wire. Now imagine we have a second wire in proximity to the first and we provide a charge to the second wire. That, of course, will give rise to a second electric field in the vicinity of the second wire. If the two electric fields are of the same polarity, those two electric fields will interact and induce a repulsion between the two wires. Now imagine we substitute the electric field around the second wire with a free space electric field of a laser beam. A laser is little more than an oscillating electric field. That electric field will interact with the first wire in exactly the same manner. As the laser passes the static electric field around the first wire, the result will be a series of tiny repulsions and attractions. The result will quickly sum to zero. But if we vary the charge on the wire in sync with the electric fields of the passing laser, we can produce a net repulsion over time. Now let's consider scalability. The example above illustrates the case of a single conductive element and a single laser pass. The next step is to construct an array of conductive elements, each driven at the same frequency and controlled to stay in phase with the same laser beam. That same laser can be directed to a subsequent set of conductive arrays to repeat the process an undetermined set of times. To put it another way, a repulsion may manifest only one instance in 100,000 laser oscillations. The conditions can be engineered to repeat the process 100,000 times on the same laser sample window. One of the more intriguing aspects of this approach is the power-to-weight ratio, achievable in current laser devices. First, let's note size. A laser package may be several millimeters on diameter, but the laser itself is much smaller, commonly just a fraction of a millimeter square. Also, current printed circuit boards have feature spacing around 1/10 of a millimeter, and integrated circuits can have feature spacings 100 times smaller than that. The net result is that the devices described in this presentation, even with meters of optical path length, can be surprisingly diminutive. Now consider power. A ridge waveguide laser just a fraction of a millimeter squared can have an optical output of tens of milliwatts. Even a fraction of that optical power converted to motive force can provide a critical means of renewable propulsion in a gravity-free environment. But perhaps even more interestingly, 50 milliwatts converted to motive force is sufficient to lift 1 gram of mass against the force of gravity at sea level. If the mass of a 50 milliwatt device is less than 1 gram, a plausible goal, an ensemble of such devices, could have substantial excess lift capacity. Our current focus is on aerospace applications, but our longer-term goals include terrestrial crafts.